Is it on 0? Okay, physical science time. Time that is for physical science. Today we're going to be talking about chemical reactions, which is kind of in the same way that maybe Newton's laws are they're certainly not the only thing we talk about when we do the physics unit, and they may not even be the most important thing, but they're kind of the central point. Like if you get the Newton's laws, it helps you get the other stuff, and if you don't get Newton's laws, there's almost no way you're going to get the other stuff. That's what this is for chemistry. Like if you get chemical reactions, it'll help you with everything else in chemistry, and if you don't get chemical reactions, your chemistry knowledge is toast. What do you say? Cooked. You're cooked. You're cooked. Okay, okay, chat, would you please tell me what the objective is? That's really cute that someone would say that on their YouTube video. Plan and carry out an investigation or investigaciones? Oh, just one. Sorry, you guys did not meet the objective. It was supposed to be one investigation. Plan, I made you. Plan and carry out investigations of, on, regarding, of chemical. Here, I'm going to do something cute, and then you need to write this down too. RXN is the abbreviation we use for reaction. Chemical reactions. This RXN is an abbreviation for reaction. I do want this picture-in-picture. Did it go picture-in-picture? Okay. So a chemical reaction, could you, using knowledge you gained earlier in the year, could you kind of, maybe not necessarily define, but could you give me the idea? Could you generate a sentence describing what a chemical reaction is? It's related to a chemical change that we have talked about. I'll give you that for free. What do you think? Well, we can't use reacting. Okay, excuse me, interacting. So let's put two or more. It could be more, couldn't it? What, did anyone do a lab that had more than one, what you might call ingredient? Yeah, in fact, you both groups, almost all your chemical reactions did. Two or more substances. Let's go beyond interacting. That is true. When they react, they specifically are doing what? Yes, exactly. Two or more substances changing their, how would we tell? Not necessarily their state of matter, but you're close. Yeah. How would we know? What would we see or smell or hear differently? Yeah, bubbles, and because something is, what, they have changed their, what things about them that we would describe them as, their properties. Exactly right. Very good. Very good. I don't even think that was an obscene amount of hand-holding. I think you just got two or more substances changing their properties. I was going to put through a process. I still could. Through a process. Now we're getting a little bit in the weeds, but relating to their valence electrons, relating to valence electrons. I'm going to put, this is all plus, plus, plus. Like two or more substances changing, that's what a chemical reaction is. This stuff is true and could be part of the definition, and you should know it, but it's not really, in the strictest sense, how we define chemical reactions. Chemical reactions are two or more substances. We might say combining, but that only certain types actually combine, but they change. It might even be one substance. I should probably actually get rid of that. Usually, and this could be in parentheses. So substance changing is kind of what we got. Substances, possibly more than one, changing. Because one of the best ways I think to do this is let's just go into some examples. Can you think of anything that I might be willing and happy to use for examples for this part? No, come on, you can do better than that. Where could I get some examples of chemical reactions? Your lab, yeah, that's why we do the labs first, is so that you have some background knowledge of things that you have done, so that we can talk about them. And so tell me about your lab activity. Mason, what did you do?
We added luminol
Mm-hmm.
and other substances.
Luminol. What else?
Luminol,
If I were going to say that I was adding,
mixing.
yeah, but if I was going to say adding, what symbol could I draw in my? We don't. Yeah, plus sign. There we go. Luminol plus. What else do we have in there? Potassium ferrocyanide. I would have to look up the ferrocyanide ion. Would someone have their phone with them? In fact, I think you might all, because no one's in the crowd. Would you real quick just type in potassium ferrocyanide? Tell me what its formula is. I'm gonna guess it's just FeCN, but I don't actually know, so I'm willing to correct that, and I will stand corrected. And I've never said I know everything. I used to have a sign right here that says I know everything, but then it said it was me, Mr. Keim, lying, and I am lying when I say that, but I know more than you. Yeah. Well, hold on. So K3FeCN6 is what I'm going to write. Would these numbers end up being right? Yeah, because they're so in parentheses. I think that's going to be right. So luminol and potassium ferrocyanide, and what else? Hydrogen peroxide and sodium carbonate, I believe. Sodium carbonate yields, well, something, and I should tell you that this means yield. So this is called a chemical, can you guess? Chemical what, do you reckon? Yes, that's true. That's not what this is called, though. This is a chemical change. A chemical change is occurring in this reaction. Substances are changing. But this thing that I have written is called a chemical guess. Chemical bonds are forming, changing, reforming. But this whole thing that I've written is a bookkeeping tool that we use called a chemical equation, yes. We call it that. It's related to math equations, plus. Except instead of the equal sign, which is kind of weird because equation implies an equal sign, we have a yield. We call this arrow here yield. I'm going to draw another arrow to that arrow, and it's called yields. Have you ever heard the word yields before? In this context, not so much like a yield sign, although I'm sure there is a relationship, but this is like when you read on the back of a box of brownies or cookie mix or whatever, and it says yields 4 dozen cookies. It produces 4 dozen cookies. The crop, Joe, this one's for you. The crop of corn yielded 20 bushels to the acre. Yield means to produce. That's what it produced. So this yield sign. And then these, I'm going to label these. What are these little guys called? Doot. Yep, I labeled them. They're plus signs. That's just the same as in math. You might remember the plus sign from when you learned math when you were a kindergartner. So in the chemical reaction, we have what they are. These, sometimes you might label these chemical species, like different things. I'll sometimes use that term, chemical species, different kinds of chemical substances. We might call them substances. And then altogether, these ones that I've written in green are what are called reactants. Reactants. The things that react. Those are the reactants. And the reactants yield, I've run out of room, but the reactants yield products. And because I'm not exactly sure in this reaction what the products were, we're going to leave that like that for now. But the reactants yield the products. Give me another example of a chemical reaction that happened in the laboratory yesterday. Elephant toothpaste. Elephant toothpaste. So what you observed was you put together a liquid and a liquid and a liquid and a powder, and it became just foam every place, right? And so you could tell, that's one of the ways that we can tell a chemical change occurred. I'm going to add that up here actually. Some of the ways that we can tell they occurred is production of gas. That's what foaming and bubbling are, is when a gas is produced. So most of these reactions that we observe, not all, certainly not all, but most of them that we observe in the lab, at least at this level, happen in aqueous solution, happen in a water solution. So if a gas is produced, we often see that as bubbles or foam because it's in water. Anyone who's ever farted in a bathtub knows that a gas in a liquid produces a bubble. Could you laugh at my joke, please? Thank you. That's better. What else might tell us that a chemical, this is a little bit of a side note, we're going to get back to what we were just talking about, but what else might tell us that a chemical reaction occurred? Color change, yep, absolutely. Now, every time a color changes anywhere in the universe, that must have been a chemical reaction? No, these are clues. They're not cut and dried, absolutely this happened. These are clues. What else? What other clues do we have? What? Yep, temp change. What else? One that we could smell. We could put taste. Why do you think I'm not going to put taste? We don't do that. But, not in the lab. But, if you, and back in the cooking one, right, cooking is full of chemical reactions. You might even call cooking at its core is chemistry. But the egg and the flour and the chocolate chips and the sugar tasted separately, taste different from cookie at the end. And all you've done is squish them together and put them in the oven. A chemical reaction occurred. They're totally different. And that's actually one of the overarching principles of this is that reactants have totally, and I mean that word, different properties. Is this showing up at all on the TV? From products. Kind of. I'll say it again so that at least the captions will pick it up. Reactants have totally different properties from products. I would not go as far as to say there would be no overlap, but in most cases there is no overlap. The classic example is sodium, silvery white explosive metal that you've seen, reacts with chlorine, poisonous gas, to form table salt, which is that little white powder that you put on your fries, right? Totally different properties. Not explosive, not silvery white, not poisonous gas, not green like chlorine is. Totally different. All the properties are different. So that's the fundamental thing. And that's one of the ways we can tell whether a chemical reaction occurred or just physical changes. Because in physical changes, like you nail a nail into a board, well, it's still nail and board. They're together in a sense, but they're still two separate things. In chemical reactions, the properties are totally different. So back to our hydrogen peroxide one, the elephant toothpaste one, we had the production of a gas, which is a clue that a chemical reaction occurred, and the products, a gas, has totally different properties from the reactants. Here's the chemical reaction for that one. You used what? What was one of your main reactants? I got my reactant color here. What was one of your reactants? In your elephant toothpaste. Soap was not one of them. Nope. The soap was just there to make the bubbles stay. Good guess. I mean, did use it. It wasn't actually a reactant. We're going to get to that in a second. What else? Hydrogen peroxide. In fact, I'll give that to you. This is the reactant. That's all that reacted in that. And this gets us to another point. So all we had was hydrogen peroxide. Did you see this, by the way? Yeah. Okay. All they had was hydrogen peroxide. That was the only actual reactant. Yields. All it actually, I'm going to switch my product's color. All it actually produced was H2O and O2. Well, now listen, that doesn't seem like the truth, right? It doesn't seem like it was just hydrogen peroxide, because the hydrogen peroxide just sitting there doesn't seem like it made these two things, right? You added what to it that actually made it go? Do you remember? It was potassium iodide, and I put that above the arrow. It was I'm going to probably do this in a different color, pink. Okay, potassium iodide. This was what we call a catalyst. Do you remember the word catalyst from your vocabulary, and what does it mean? It speeds up the reaction. So this wasn't actually a reactant. It wasn't, the way we can tell is that if we went back, we could actually, if we let it dry up, we could scoop all the potassium iodide, every single molecule of it. It's not covalent, so every single formula unit, we could get back. None of this was used, we might say, in the reaction. None of this wasn't actually reacted. It just made it go faster. So this reaction, even without the potassium iodide, just happens. all the time that you have hydrogen peroxide, it becomes water and oxygen gas. What do you, can you think of a piece of evidence that supports that all the time hydrogen peroxide just becomes these two things? Maybe very slowly. How did we store, there are two pieces of evidence I'm looking for. One, how did we store it? Do you remember? In a brown bottle. And in the case of the strong hydrogen peroxide we use in your second one, an oversized brown bottle. Brown. So when you buy hydrogen peroxide at the store, it's brown so that light doesn't get in, because light can speed this reaction up. Light can catalyze, we might say. And when we buy the strong stuff, it comes like this, like there's just extra room up here, because one of the products of this reaction is a gas. And so just sitting there, there's another piece of evidence, just sitting there, this reaction happens. What's the other piece of evidence that that is probably true? You heard me say this several times yesterday, that hydrogen peroxide is old. Did you say old? You didn't. You just said but I thought you said old and now I gave it away. It's old. If you let it, if this goes on long enough, it just doesn't, it's just not hydrogen peroxide anymore. It's now water and oxygen gas, which have completely different properties from hydrogen peroxide. So just sitting there, this reaction happens all the time. The oops, I'm going to do this in my reactant color. Just sitting there, the H2O2 becomes H2O and O2, just all the time. Now, all you did in your reaction was catalyze it. You made it go faster by adding the potassium iodide. Light makes it go faster in this case. Potassium iodide makes it go faster. Some metal, silver, makes it go faster. In fact, this is kind of cool. Some of the rockets that they use on the space shuttle, specifically ones that for station control, like turning it or moving it, you can't just like, if you're driving a car, you use friction to turn. You turn the wheel and the tires move, and so friction causes the car to turn. If you're on a boat, the rudder causes a change in the stuff, but there's no stuff in space. And so what they do is they have little rockets, and those rockets actually just do this. They just have a tank of hydrogen peroxide, and they pass them through a silver mesh, and it instantly becomes this, which is a gas at the temperatures that this is happening, and this, which is a gas. So this tank of liquid just becomes these gases, and then that's like a rocket. Anyway, so this reaction is always happening. We catalyze it with the potassium iodide. What was the point of the soap? You didn't need the soap. The soap was just there so that the bubbles would stay, so it would look like toothpaste. And what was the point of the dye? Just to color it. And so those weren't actually part of the reaction at all. 2 points I want to make. One, this is just substance, not substances. One thing can undergo chemical change to become two things. Okay? We'll talk about the types of reaction here in a second. And another thing, astute observers of mathematics will know that something ain't quite right here. Do you see a problem with this equation?
There's three options.
Yeah, exactly. So on this side, when I say side, I'm talking about on either side of the yield sign. On this side, there are two hydrogens. On this side, there are two hydrogens. On this side, there are two oxygens. And on this side, there are three oxygens. So something's wrong. We'll fix that in a second. First, we're going to talk about the types of reactions. You need to know the four basic types of reactions. Excuse me. 1, 2, 3, 4. In your notes, I expect to see a list of 4 kinds of chemical reactions. And then we'll also have an example for each. Actually, I don't want to do it like that. I want to say not example next. Erase. If you already wrote example like I did, erase it and write general form. General form. And then we'll do examples. And we'll just write them right over top of what we were already doing. That seems like a really reasonable thing to do. The first kind, these are vocab words. Please tell me. You should know because they were vocab words. What's a kind of chemical reaction?
I know all of them.
He knows all of them. Just like me, I know everything. We'll say one. Come on. You have your vocab.
Chemical.
Not wrong, but that's not what I'm talking about. These are specific types. So I just asked you, what are some makes of car? And you said, car? Yes, you're not wrong, but what? What did you say? No, we're going to talk about that. Those are a different way of categorizing. We're going to talk about that in a second. Okay, decomposition. Let's put that as number 2. Decomp. I'm just going to abbreviate it, decomp. In a decomposition reaction, some substance AB yields A plus B. An example of that? The hydrogen peroxide. Hydrogen peroxide yields water and oxygen gas.
Said
synthesis, that's number 1. These don't have an actual order. Like, it doesn't really matter, but I'm used to writing them in the order I'm going to write them. In synthesis, it's A plus B, 2 separate things come together to yield another thing. Trying to think if you guys, I wanted all these examples to be from your labs. Yours is a kind of complicated reaction. So we're done using that as an example. You have seen this before. Oh, no, I have a great example.
There's way more than 4.
No, 4 is what we're going to do. I have a great example. You've seen this before. Hydrogen gas plus oxygen gas yields, what do you think? If we have a balloon of hydrogen and we light it on fire in an oxygen environment, what do we make? Almost the opposite. Aristotle would say the opposite. Water. Yeah. You don't think that, but we'll do this in the lab if there's time today because it's really exciting. And another thing is that you'll notice smear of water. It comes out as steam because it's very hot, but it'll pretty soon condense and there'll be water everywhere. Decomp is an abbreviation for decomposition. H2O2 yields H2O plus O2. I'm going to put a squiggle down here and put combustion, and we'll talk about why in a second. Another one? Single displacement, we usually call it. I think your book might call it replacement. I can't remember. I think your book calls it displacement and the chemistry book calls it replacement. Those words are used interchangeably. Single replacement or single displacement. And then its friend, double displacement or double replacement. In a single displacement, it's in the form AX plus B yields BX plus A. Kind of ran out of room. And in a double, it's AX plus BY yields BX plus AY. This one, the kind of scummy example I usually use, although I'll flip it on its head because you're boys and so I won't be misogynistic. The kind of scummy example I use is if there's a chick with a boyfriend, the chick is X and the boyfriend is A, and a hotter guy comes around, B, she's like, see ya, A, I'm going with B. And that's the single displacement. There's a list in order. I think it's in your book too. There's a list in order. Yep. On page 643, there's a list. Show it to the camera. Is that on camera? That list on the top. With the blue arrow. Boop. Okay, that. You meant left? Now it's on there?
Now it's right there.
Okay. So anything higher on the list, in my analogy, think of that as the hottest guys are at the top. Anything higher on that list will replace anything lower. The chick wants to be, I shouldn't say chick, that's misogynist. The person, there, okay, yeah, let's just take gender out of it altogether. This is 2020 freaking 5. The person, X, wants to be with the hotter person, B, than with A, because B is, in this case, lower on the list. And that's how we do those reactions. An example of that, your thermite reaction you were going to do, you had iron oxide and aluminum yields aluminum oxide and iron.
What's the product of
The oxygen would rather hang out with aluminum. It's higher on the list. And so it does. It switches. Single displacement. AX plus B yields BX plus A. Yeah, I smooshed it in and then I moved it, so I'll erase it and start over. BX plus A. And then in the bottom one, it's like swing your partner round and round. They both switch partners. And so an example of that would be like, I'll just use the one, we might do this in the lab sometime, but if we have potassium iodide plus lead nitrate, we now have lead iodide plus potassium nitrate. They switch, and the way that these occur is if one of these things is a gas or water or insoluble, lead iodide is insoluble, meaning it doesn't dissolve in water. It'll just kind of, let's get back to our list up here actually. That's one of the other main ways, and maybe the final main way we can tell if a reaction occurred, is the production of a precipitate. Was that one of your vocab words? Precipitate? precipitate means to fall. Have you heard of precipitation? What's happening when the sky precipitates? Rain or snow or sleet or hail fall from the sky. That word precipitate means fall. You might be aware of the word precipice, which is another kind of old-timey word for a cliff. Precipitate means to fall. And so when a precipitate forms, a solid is falling out of solution. That's the sound of a solid falling out of solution. I put Ki. It's Ki. It's potassium iodide, and so the I is capitalized. And then I put combustion with a squiggle. Combustion can be any of these, but it's specifically, you know the word combustion means like start on fire, right? You've heard that before. Combustion means something combines with oxygen, releasing heat and light. What do we call heat and light when they're released in a chemical reaction? That's looking like a heat and light released in a chemical reaction is looking like a, no, it's more mundane than that maybe, more caveman-y. Fire. Thank you for saying it so low and scary almost. Fire. He's trying to say it like Johnny Cash about the burning ring of fire. Any fire you've ever seen is a combustion reaction. The Bunsen burner in your lab, actually you didn't even know this was one of the examples, but that combustion, or that Bunsen burner in the lab, an example, was methane piped in from the lab, combined with oxygen in the air, right? That's why you have both a gas, CH4, and an air adjustment on the Bunsen burner, yields H2O and CO2. Did you see water produced by that Bunsen burner? Why? It was. Why did you not see it? It was hot. It was 1,300 degrees. And when water is 1,300 degrees, that's a gas. It's an invisible gas. So water was produced. In fact, if you do this reaction with the Bunsen burner and you put like a bowl of ice way above it, it'll seem like the ice is just sweating, you might say, like you have a cup on a hot day, but it's actually collecting the water from this reaction. Then did you see the CO2? No, because that's an invisible gas too. So this looks like there's no reaction at all occurring, but actually these two are being produced. And now you'll see, even though this is combustion, it combined with oxygen to release heat and light, it's also what? It's also kind of a single displacement, right? So combustions are always one of the other types too. What? Combines with oxygen to releasing heat and light. That is one of the messier handwritings I've ever done. So every kind releasing, I'll just write it the exact same way, maybe even messier, releasing heat and light. So every reaction, those we did in the lab, those you see in the land, those inside your body, are one of these types. They get more complicated, but there aren't really more types. Combustion, as I said, they're all one of these types, but they could also be combustion. They could also be, you have these other vocab words, endothermic and exothermic. Those are not separate kinds of reactions. Any of these kinds can be either endothermic or exothermic. What do those mean? Endothermic means it's doing what with thermos, heat? It's absorbing heat. If the reaction were absorbing heat, what would that feel like if you put your paws on it? No, if it's absorbing heat, it's taking heat away from your hand, it feels cold. What if it's exothermic? That means it's doing what with thermos, heat? It's releasing, it's externaling heat. And what would that feel like if the reaction is giving off heat to your little paw? It would feel like hot. This one that we did, I'm pointing out the green and brown one now, the hydrogen peroxide one we did yesterday, releases a lot of heat. We used boiling, we're not supposed to say that, we used almost boiling hydrogen peroxide to make it go faster in the first place, but also the reaction itself produced more heat. Now, we do have enough time. The thing that you'll be doing on your worksheet and the main thing that we do, like not quite math, but the activity that we do for this in this lesson is called balancing equations. You'll remember earlier I asked you, what's the matter with this hydrogen peroxide and water one? They don't match, right? Somewhere, let me erase some of the stuff around. Does everyone have what I wrote in black?
Yeah.
Okay, I'm going to erase. Thank you. Good job, Courtney. I'm going to erase what's in black over here. I'm going to erase all the examples that I had. although we could balance those too. I'm going to give myself some space. Yes, space for me. Erase this as catalyst, and we're just going to be left with just this chemical reaction. We'll do another example after this too. But you'll see this, as it is written right now, as it's kind of written, except I erased part of the two, this violates what law of the universe? Yeah, matter can't be created or destroyed. In this case, it looks like matter was created. An oxygen violates the, what do we call that guy though? I'm going to put in cursive because it's fancy. Law of conservation of mass. Ether's fine. We usually call it the law of conservation of mass. And so, in reality, we know it didn't. The way we've written it does violate it, but we know that didn't actually happen. And so we balance it. We change the numbers so that they can match. And now, the only way we can do that is by changing how many of each thing. We can change, in order to make it satisfy, in order to make it not violate the law of conservation of mass, we can only change the coefficients. What's a coefficient in algebra? If I have this equation, x plus 3, and I want to put a coefficient of 4 on it, what do I... Yeah, it's just... I mean, I guess I would... If I want to put a coefficient on the whole thing, a coefficient is a number we put out in front that multiplies everything by that. So, what could I multiply here to make this work? I can only put in coefficients, so I'm going to show you. I would put a 2 here. That makes it now 2 oxygens plus 2 oxygens is 4 oxygens and 4 hydrogens. And on this side, we have 2 oxygens and 2 hydrogens. So all I got to do is, so I can only put in coefficients. When you get your worksheet, you'll see it's chemical reactions with little blanks in front of every species, and then you put coefficients in to balance it. Now let's check it out. On the reactant side, what's in green, the left side, almost always the left side, we have 4 hydrogens, right? 2 times 2 is 4. You see that? You see that? 2 times 2 is 4. You see where I'm getting 2 times 2 from? And how many oxygens do I have? Well, 2 times 2, right? This coefficient applies to everything, is 4. So on this side, I have 4 hydrogens and 4 oxygens. And on this side, I have how many hydrogens? Yeah, tell me what math you did. 2 times 2 is 4. And then also I have how many oxygens? 2 times 1 is 2, plus 2 times, but this, there we go. So that's, on this side, 4 hydrogens and 4 oxygens. On this side, altogether, 4 hydrogens and 4 oxygens. And so now it doesn't violate the law of conservation of mass. It is happying the law of conservation of mass. And so we change these coefficients to make sure they balance. We'll do more math with that. That's what your practice worksheet is about, is this. But I also want you to identify which of them on your worksheet. I think I'm going to have you do it different. I'm going to have you name everything, because I think you still need work with naming that we did in the last chapter. I'm going to have you balance it, which is the main point of the worksheet, and then tell what kind it is. So for that one, we would write hydrogen peroxide, water, oxygen gas, and then we would write what kind of chemical reaction is this? Decomp. We would write decomp. You might even just write the letter D. So it's a decomp reaction. So those 3 things you will do with it. Water. Yes, we will. Let's. We might have to do it tomorrow. I really got 10 minutes. I think that's good. You have. Yes, you had a question. Oxygen gas. Does anyone else have questions? So the main thing to do is balance these so they satisfy the law of conservation of mass. Also determine what kind they are, and then as long as you. I shouldn't say as long as. There's a lot of stuff we should know, but the main things are those 2 things to do, and then the things to know are clues about when a chemical reaction has occurred, and the general definition of what a chemical reaction is. Yep, the worksheet is just balancing, but I also want you to name them from the last chapter and write the kind. And then on the test, it'll be those, and then concepts about, like conceptual questions about such and such has happened. Did a chemical reaction occur based on the clues? Or what is the definition of a chemical reaction? Or some stuff like that. Other questions? Thank you for your questions. Other ones?